Hi, in this video we're going to continue to talk about binary search, specifically its interface and performance. Alright, so one kind of odd little thing that hopefully you also find it kind of odd is when I call the binary search, I have to tell it 0 and length minus length of the list minus 1. That's like, ooh, ugly, right? Because remember, when we do the linear search, all we have to do is give it a list and give it a key. We don't have these funky lists, funky whatever index that we have to supply and all that, right? So we really want to do the same thing here for binary search, that we don't really want the caller to have to give it the start index and end index, right? So how do we achieve that? So what we can do, remember our goal. We have actually two goals here. First is we don't want the caller to have to specify the end and the start and the end index. However, in the recursive call, we definitely want to tell the recursive call where to start and where to end so that we can shrink the list. Right? So how do we achieve that? Well, the way to do it is with default values. So we can actually say, in order to eliminate this, we can eliminate it, but we still want to keep the parameters around, so we have to give it some default value. Let's give it none for both of them. Right? So, but that means if they are none, then we should set them to the proper value. Right? What are the proper values? I'm going to get rid of this now. So if I know start is none, oh, by the way, we probably never, I think we haven't talked about is, so I'm going to just use equal to none. Okay, if start is none, then we know it's from a client call. So we know in this case, start should be 0, right? And the end should be the entire length of the list and minus 1, because that would be the last element. So that would be that, right? And then when we do the recursive call, then we specifically, explicitly specify what the start is and what the end is. In that case, the start is not none, and we're not going to change the start and the end. So the start and the end would be whatever the recursive call has specified. So we kind of handle both cases now. And hopefully, if we do this right, this is still working exactly the same. So let me run this. And there. It still works the same way, right? We still find every number, and when we look for the number 70, we didn't find it. Okay, so that's what this slide is about. Okay, so finally, I want to talk about performance. Right? Remember, the whole reason we say we want to do binary search is it should be a lot faster for a sorted list anyway. So how fast is it really? So let's say let's say your element had, let's say the list has 64 elements. Not an array, apologies. Let's say the list has 64 elements. In the first round, how many elements are eliminated? Well, half of them, right? So in the first round, 32 elements are eliminated. In the second round, with 32 elements left, how many are eliminated? Half of them, 16. Third round, 16, half eliminated, 8 of them are eliminated, so on and so forth, right? So if you kind of do the math, then how many rounds does it actually take to find what we're looking for? This requires a little bit of math, but hopefully it isn't too hard. The answer is really log to the base 2 of 64, and that's about 8 rounds. Plus or minus 1. It might be 7, might be 8, but it's the exact number is not important, but the important thing is that in this case, given the list has n elements, it takes on the order of log base 2 n comparison, or to find the key. So in terms of the big O that we kind of talk about in the linear search, this is big O of log n on the order of log n. So again, we'll talk more about this in class 3C, but this is just a preview. Okay, so now here's the fun part. If n is a million elements, if you have a million elements, the log base 2 of a million is only 20. Okay, compared to, if you remember, for linear search, it's 500,000 on average. This is only 20 comparison on average. So it is a lot faster. So binary is really a lot faster than linear search. And to prove that to you, I actually wrote a little timer. Well, I didn't really write the timer, but okay, I don't need this whole thing anymore. I don't need this. Okay, so I have a little performance comparison here. And let me explain that. So I create a list. This list has, let's see, 10 million numbers. And they are sorted. So it's just I for I, meaning this list is just 0, 1, 2, 3, 4, 5, all the way to 10 million. The key I'm looking for, I have it set up on a million. Okay, so it's not at the beginning, it's not any in the end. So it's kind of just kind of a random million number, the million place. Now, there is a way to measure how long a particular function or a particular task take. And that's actually in one of the assignments, how we measure things. But if you didn't do that part of the assignment, it's okay. But basically, I do a time.time. So what this returns is a floating point number that represents the current time. So I remember the current time, and then I do my linear search of key 1 million in the big list of 10 million numbers. Okay, I want to make sure that, yeah, it kind of finds it. It should be at index 1 million. Okay, and then after I do this linear search, I'm going to do the time again, which is going to give me a new time. And the difference of this new time compared to the original time would be the duration, would be how long it has taken. Okay, and I'm just going to print out the duration. All right, so this is how this works. I'm going to run, I'm going to do exactly the same thing, but also for binary search. Okay, so the only difference between these 4 lines and these 4 lines is really, one is doing binary search, the other is linear search. Everything else is the same thing. Okay, so I'm going to run this. The linear search took a while, but it's done. Okay, look at the time that it takes here. The time that it takes here for linear search is 0.1 seconds. Look at the time that it takes for the binary search. It's a really, really small number compared to this. So there, this is a proof. This is proof that binary search is really much, much faster than linear search. Okay. All right. I think that's the end of the video.